Giving you a brief introduction about our organization, Pune Knowledge Cluster has been established by the Office of the Principal Scientific Advisor to the Government of India. It aims to bring together academia, R&D institutions and industries in and around Pune to address some of the challenging problems of the region through innovative means, using scientific approaches and engaging highly skilled human resources. We host this monthly talk series as part of our Vigyan mentorship and scholarship program, which is an initiative for promoting chemistry amongst young women. This program is supported by BASF Chemicals India Private Limited, and it is implemented by Pune Knowledge Cluster since 2022. Through this talk series, we aim to bring forward the journey of leading women in various fields of science, technology, engineering, and mathematics. We hope this initiative will inspire young women to break gender stereotypes, societal barriers, and encourage them to pursue careers in STEM. I take this opportunity to briefly introduce our speaker to you all. Dr. Fatima Jalid has been working in the Department of Chemical Engineering, NIT Srinagar, since January 2016. She completed her BTech in Chemical Engineering at NIT in July 2015. Thereafter, she started her MTech in Chemical Engineering at IIT Delhi and also got selected for the prestigious Trainee Teacher scheme by MHRD. So she started her teaching while simultaneously doing her doctorate. Her work is focused on computational catalysis, specifically on understanding transformations of hydrocarbons using ab initio microkinetic modeling, and her research has been published in high-impact journals. He has been an ardent educator and teaches a variety of courses at NIT, which includes advanced mass transfer, chemical reaction engineering, and energy technology. Dr. Jalid has a young yet incredibly successful career. Her list of accolades include the Gandhian Young Technological Innovation Award in 2018 for her research in biomass-derived platform chemicals, the Valloway Women Scientist Award in 2022 for her achievements in her research. And this year, she has been selected as one of the 75 women in She Is 75 Women in Chemistry by Beyond Black in partnership with the Office of the Principal Scientific Advisor, Government of India, and Royal Society of Chemistry. Dr. Jalid hopes to use her expertise in addressing the Sustainable Development Goals by exploring alternative energy technologies and materials that can catalyze reactions towards creating a greener world. She envisions to apply her knowledge and skill for resolving problems related to the changing physiochemical characteristic of the Dal Lake water in the future and focus on finding solution towards local problems. Her talk today is titled Beyond the Reaction, Catalyzing Change with Purpose and Persistence Towards a Sustainable Future. Now, before we get started, I'd like to give you a few instructions for the session. We will be having a 45 minutes presentation by our guest speaker. This will be followed by a moderated session. After that, the session will be open to the audience for Q&A. With this, I extend a warm welcome to Dr. Jalid and invite her to take the session forward. Over to you, Fatima.
Thank you so much, Ritika. Thank you for the kind and humbling introduction. So, I'm Fatima Jalid, and I'll be talking to you all today about Beyond the Reaction, Catalyzing Change with Purpose and Persistence Towards a Sustainable Future. So, over here, I'll be sharing snippets from my professional journey as well as research to give you some guidelines on how to go ahead with things. So, the start of it, these all pictures, basically, this is where I'm from. I'm from Kashmir, and I've spent the largest fraction of my life in Kashmir itself. So, I did my schooling from Presentation Convent High School, Srinagar. That's where I did my 10th boards from. After that, I took up mathematics as my subject in my 11th and 12th class, and I did my 12th class boards from DPS Srinagar. Now, during my school years, I really, really loved learning. Learning was like, it was something like me as a scientist going on to unravel new things and understanding key concepts. It was more like I was the detective on to finding different cues, which helped me understand, different laws which govern the universe around us. So learning with me it was like a spark of joy within when I understood things. Maybe it was because of the way my mother used to teach us when we were kids. She used to make very complex things. She had a knack for it. She used to make those complex things very simple for us to understand. And that is the beauty of understanding and reading basically. When you understand something, when the meaning unfolds, you see that it is also very simple. And in the simplicity of that answer is utter beauty. And that is what my school years were mostly about. I really liked reading. I read beyond the text. I also loved reading other things. I read Harry Potter, Agatha Christie, and Paulo Coelho, and all the different books. So I really liked reading. And more so, I loved understanding things. I loved looking at nature and trying to, fathom what's happening behind. And after that, as was the general trajectory back in my time, after my 12th boards, I gave the AIEEE examination and I got selected in the Department of Chemical Engineering at NIT Srinagar. So back then, I did not have much idea on what chemical engineering is. In fact, it was the engineering stream of which I did not know as much as we know about like civil engineering, electrical, mechanical. So I won't say that I always had my goal like BTech chemical engineering. This is something I'm going to do. I liked studying, I liked understanding things, and this is what I ended up doing. But as the name says, chemical engineering, one might think it's just chemistry, but it was beyond chemistry. It was like the physics of dealing with different kinds of chemicals and how they operate and everything. So chemical engineering also satiated my love for learning and knowledge and understanding things. So I remember in my second year in this department where I'm working right now in chemical engineering, our teacher gave us a paper reading assignment. So it was my first step into research, and it was just amazing. I remember I had a paper to read on activated carbon, fabrication of activated carbon from coconut shells. So basically, activated carbon is a good adsorbent, which means it has a very high surface area. And that paper just talked about how they made activated carbon from coconut shells. And reading that literature gave me a feeling of, I'm understanding new things, I'm exploring, and that feeling was really amazing for me. So the next exposure to something, so research was in my final year BTech project. So as it says over here, my dissertation was based on activated carbon from almond and walnut shells. Now it seems very simple, right? It seems like, yeah, okay, instead of coconut shells, now what I'm using is almond and walnut shells. And me and my team, we were doing rigorous experiments on this, but our surface areas were not coming out as we had expected. When you try to make activated carbon, the goal is that you have to make a good adsorbent. And the property of the adsorbent has to be that it has a good surface area. But surface areas were coming out really, really poor. So how we did it was we had, let's say, walnut shell, we crushed it, then we passed it through a mesh, then we dried it up, then we activated it chemically with zinc chloride, and then we had to wash it. And repeatedly, we were getting really bad results. We were not getting what we were expecting, a high surface area. So then I read a lot of literature on it. I read papers and we went back and forth between experiments and reading and understanding those things. And we realized that we were missing out on a simple washing step. After activating our walnut and almond shells with zinc chloride, we were not washing that zinc chloride off it, leaching it out of the system. So what was happening was all the area which was created, the surface area which was created by means of our experimentation was covered with the zinc chloride itself, and there was no surface available for adsorption. And that is why we were getting such poor results. So when we fixed that up, we got amazing results. And this just gave me a glimpse of what research looks like. Research is not you getting the results. It's the path you choose to get the results, which shape you the way you are, which shape you the entire process shapes you eventually. So while I was doing my BTech, in my final year, I gave this GATE exam and I got selected for MTech at IIT Delhi and IIT Roorkee. So again, I won't say that I had in mind that I had to do PhD and then I want to become this, this, this. All of those things just came along the path. But I think I was persistent, and I was consistent. And those qualities, hard work, I also put in some hard work. Those qualities really helped me get where I am. And obviously the support of people around me, that's the most important thing. So then I gave the GATE exam and I got into IIT Delhi. I went for MTech to IIT Delhi in chemical engineering. I graduated as a valedictorian in IIT Srinagar. So then I joined July 2015. I joined MTech in chemical engineering at IIT Delhi. Now over there, I was studying. It was the first time I was earning some money, also the stipend, and then I was a TA. But in the meantime, NIT Srinagar floated an advertisement for the recruitment of trainee teachers. So it was a scheme by MHRD, which every NIT was implementing throughout the nation. And it was basically a nationwide call to recruit trainee teachers. Now, the thing was, those people could apply for it who were like in the top 10% of the class or had qualified and were from CFTIs or had qualified GATE. And there was a written test, and then there was an interview which was held at IIT Delhi. So now the person who would be recruited as training teacher had to do two things. The person had to be a full-time teacher at NIT Srinagar, and then the person had to do a PhD from IIT. So NIT Srinagar happened to have the MOU with IIT Delhi. So the person who gets selected, who gets the offer letter, has to do his PhD or her PhD from IIT Delhi. That was the thing. So I was very confused because I was already doing my MTech in chemical engineering at IIT Delhi, which was a wonderful opportunity. And I got confused whether I should apply for it or not. But then I did apply. And then I got the offer letter for it. But I was still a bit confused because I was already doing there. And then I could have gone somewhere else, maybe outside for my PhD, if at all that would have been in my mind. So I did this prayer called istikhara. It means basically just take help and you just pray to God to show you the way through and everything. And that's when I signed up for Trainee Teacher scheme. So after getting the offer letter, I signed up and I gave my acceptance for it, and then I started my career as a trainee teacher at MIT Srinagar. What it meant was that it was in January 2016 that I started this. Up until that, the recruitment process was going on, and I was also doing my MTech first semester at IIT Delhi, which I had to leave then. So I had to do my PhD from IIT Delhi, which I started off at the Renewable Energy and Chemicals Lab under the guidance of Professor Ali Haider at IIT Delhi in 2016 January. So this was a completely different thing. I had not envisioned it ever, that I would end up doing such a thing, because it was a lot of workload. We did not just have to do, it was not just the doctoral research that I had to do. I also had to teach courses in NIT Srinagar, which was pretty taxing. And at the beginning of it, obviously, I did not have any exposure teaching. So the first year, it went something like this. The first year in 2016, I had to do my coursework, which I did from IIT Delhi. And from 2017 onwards, I have been teaching at NIT Srinagar. So the only time we got for research was in the winter months when it's very cold over here and we have vacation. And I used to go to IIT Delhi to do my research. And then besides that, I had to shift between multiple roles on an everyday basis. Like I had to do my research, I had to report to my supervisor on my progress, I had to teach courses at NIT Srinagar. I also had to do the departmental admin workload and everything. I had to supervise my students. And it was pretty taxing to navigate between these roles. But thankfully, with the help of people around me, I was able to get through. So, but the thing is, what was required was flexibility and fluidity to move between these things. And even so, up until this point, I had to be flexible in accepting the different things that came along the pathway. So then at REC Lab at IIT Delhi is where I learned everything about my research. I started working on computational catalysis over there, and I also started running some experiments on electrolytic purification of biomass. Now, as Ritika mentioned, that I had to do ab initio microkinetic modeling, wherein I had to test, not experimentally, but computationally different catalysts and see how they perform for various kinds of reactions. And then we also augmented that with machine learning techniques in order to reduce the computational time as well as cost, and to come up with the novel alloy and catalyst formulations for different processes. My dissertation was entitled First Principles Design of Transition Metal Catalysts for Selective Transformation of Hydrocarbons. I'll be talking about what I did in the course of, my PhD also. But all of it required me to be flexible, as I mentioned, and then I had to read a lot. Then I had to read myself to teach my classes, and I had to manage different roles. But with the help of that training, that rigorous training which I got from my supervisor, as well as from the department here at IIT Srinagar. And the knowledge that I gained through the course of my PhD, I was able to establish my own lab, my own research group here at IIT Srinagar. So it is called Catalysis Laboratory, wherein I am trying to, use this ab initio microkinetic modeling for different kinds of reactions. And my goal eventually is to come up with the best catalyst for different reaction steps, wherein I can set up small experiments for them in order to test them. So whatever I do computationally, I want to test those things experimentally. Currently, I'm supervising 3 PhD students. So currently, the research going on around the world is basically focused on the Sustainable Development Goals laid out by the UN. So there are a total of 17 SDGs, as they're called. The first one is no poverty. Second is zero hunger. The third is good health and well-being. Fourth is quality education. Fifth is gender equality. The sixth one is clean water and sanitation. Seventh is affordable and clean energy. Eighth is decent work and economic growth. Ninth is industry, innovation, and infrastructure. The 10th one is reduced inequalities. Next is sustainable cities and communities. The next one is responsible consumption and production. 13th is climate change. 14th is life below water. 15th is life on land. 16th is peace, justice, and strong institutions. And the last one is partnerships for these goals. So in my lab and throughout the length of my PhD, the problems that I worked on, they're centered around these sustainable development goals. The first one being clean water and sanitation, the next being affordable and clean energy. Third one is climate action, and lastly, it is responsible consumption and production. So largely what I've done during the course of my doctorate and after that with my students here at IIT Srinagar, it is the in silico screening of materials for various applications like you see listed over here. For instance, there is CO2 assisted alkane dehydrogenation. So the reaction that I did, this is the work that I did in the course of my PhD with Professor Heather. So alkane dehydrogenation, for instance, I have ethane, I have to dehydrogenate it to form ethylene. Now, conventionally, that ethylene is formed from shale gas and oil reserves and everything. But in order to circumvent that route, we thought, how about we use CO2 assisted alkene dehydrogenation. So in this case, I do form ethylene, which is a precursor towards the production of polyethylene with the help of CO2. So when you use CO2, you basically help address this climate action because CO2, when used, reduces the carbon content in the atmosphere. That therefore reduces the greenhouse gas effect, thereby reducing the global warming and bringing down the temperatures. Then the production of polyethylene basically helps you in responsible consumption and production, right? Because you try to use routes which are more environment friendly. The next reaction over here is hydrodeoxygenation, which is basically centered around molecules you get from the fermentation of biomass. So these platform molecules which are obtained from the fermentation of biomass, they can be converted to different chemicals. And one of the ways to do it is hydrodeoxygenation. Hydrodeoxygenation basically means deoxygenating any chemical compound in the presence of hydrogen. And we did make models on it, and we tried to come up with novel catalyst suggestions. Then biogas reforming is again a wonderful way to convert your biogas towards the production of towards production of synthesis gas. And synthesis gas has wide applications worldwide. So then we have aqueous phase reforming, which is again deals with the conversion of biomass-derived molecules to syngas directly in a one-pot synthesis. Like the temperatures are low and it's done in an aqueous phase. It's a wonderful reaction which does not require much energy input. Then water gas shift reaction, one of my students is currently dealing with, trying to understand the mechanism of the reaction and different insights into the molecular simulations. Then there is non-oxidative dehydrogenation. And one of my students is working with CO2 captured by amine solvents. So amines usually react with the CO2 and they form a zwitterion or they form a carbamate species. And that's what one of my students is working with. So my goal in this lab, in establishing this lab, is to do in silico screening of different materials for wonderful applications, and then eventually testing those experimentally. That is what I'm trying to set up in my lab here at IIT Srinagar. So to understand the work that I've done, let's analyze this simple reaction. The molecule we see over here is ethanol. Now we see that ethanol on CO scission is producing ethane. However, if the CC bond breaks over here, it's forming just methane. Now, if I want my product, if I want a fuel-like product, I want to retain the carbon chain length, because higher carbon chain length means I have a good fuel, right? But also, if I want a good fuel, I want to remove this oxygen from it, because oxygen reduces the calorific value of my fuel. So when I'm working for this, I am trying to figure out what catalysts am I going to use for this reaction. And I want catalysts which retain the CC bond if I'm trying to make a good fuel, and which break the CO bond. So this is my product of interest, let's say, over here. Now, essentially, what a catalyst does is it provides an alternate pathway for the reaction to take place. Let's say this reaction is taking place over here, but the dotted line shows a reduced activation barrier for the reaction. So basically, the usage of catalyst allows the reaction to take place by an alternate route, which does not incur as much energy, activation energy. So this is basically hydrodeoxygenation reaction, which I was just talking about. In the presence of hydrogen, you're just trying to remove the oxygen from it, and you want to retain the carbon chain length. And these are the catalysts we found to be good for it: cobalt, ruthenium, rhodium, and nickel. But anyways, that's beside the point. What I want you to appreciate right now is I want to figure out the best catalyst for this reaction. Now, experimentally, if I had to do it, I had to go ahead with high throughput experimental catalyst screening. That involves the automated preparation of catalyst, which is to be followed by the catalyst characterization. Now, once the catalysts are characterized, you have to screen them parallelly in different reactors. And upon the completion of the reaction, there has to be product analysis for us to understand the activity and selectivity of different catalysts. This is how it occurs experimentally. For the automated preparation of catalysts, there is either an automated liquid handler or pulse laser ablation technique, by means of which multiple catalysts are synthesized parallelly. Now, once the catalysts are synthesized, they are tested, as you see over here. They are tested, they are characterized for different properties. You do TPD, TPR, XRD, there are so many things, TEM and everything. And then you do that and you get to know the properties of the catalyst that you're making. And it's going to be like hundreds of catalysts, right? Or maybe let's just take the number as 50. Then we have to test those catalysts in these multi-channel monolithic reactors. So every hole that you see over here, that's channel, that's cylinder, which is filled with a different catalyst. And once the reaction completes, you have to analyze the products, right? And for that, a mass spectrometer may be used, and you can figure out which catalyst has a higher selectivity or activity. Now, in my PhD and after that, what I've been trying to do is I've been trying to demonstrate kinetic modeling as a way to do this high throughput screening without having to do actual experiments, without having to do actual characterization or the reactions or the product analysis. So by circumventing all of that, what we have been trying to do is use kinetic modeling as a way through. So traditionally, kinetic modeling is done based on different models. For instance, the most common is the Langmuir-Hinshelwood model. This is the Langmuir-Hinshelwood model. This is what it looks like. The assumption is made that the reacting molecules come and sit on the catalyst surface over here. Then the two molecules react on the surface of the catalyst. Then the product so formed dissolves from the catalyst surface. So this is what Langmuir-Hinshelwood model suggests. And then there is generally assumption of rate determining step. Rate determining step means that one of the steps is so slow that it governs the rate of the entire equation. The rest of the steps are so fast that they won't affect the rate of the overall reaction. Now, these assumptions become necessary when you're trying to run experiments, because you cannot experimentally measure all the variables. That is not possible, and therefore such assumptions have to come into picture. But in the kinetic modeling that I have implemented in this work, there is no assumption of rate determining step or most abundant surface intermediate or nearly empty surface. Herein, all the problems that I'll talk about, we have solved all the rate differential equations numerically under steady state approximation. Steady state approximation says the coverages do not change with time. Now, what is coverage is, let's say if I have this is my catalyst surface, and these molecules are sitting on top of the catalyst surface, they basically represent the coverage. The coverage means number of occupied sites divided by total number of sites. So if all sites are covered, it means the coverage is 1. If none of the sites is covered, it means the coverage is 0. It's basically fraction. So we solved all these rate equations for every single step, taking this assumption that theta does not change with time. Then based on this, based on the results we get upon solving different equations, what we see over here is a Sabatier plot. So we have tried to define the turnover. The turnover is basically the rate at which product is formed per unit time per catalytic site, okay? So we have tried to represent that with respect to certain descriptors. Now, certain descriptors would be the adsorbate energies, the energies of adsorbate when they adsorb on the surface of the catalyst, that energy. Now, if the binding is too weak, which means the reactants are not even binding to the catalyst surface, the production rate will not be high because the rate will be limited by adsorption. But if the binding is too strong, there is another predicament now. The products won't even desorb from the surface because they're so attached to the surface, and the rate limiting step will be desorption. Now, when the two are in perfect balance, that's when you reach the Sabatier maxima. And that is when the binding is optimum. Now, I must mention here that the energetics, the descriptors, the energies of adsorbates, and all these we get from density functional theory calculations, which have been performed on high performance computers. So none of the experiments have been done physically, it's all computational. So this is computational catalysis basically that I'm talking about. So now we see over here. So we see the catalysts are over here, some catalysts are on this side, some are desorption rate limited, some are adsorption rate limited. And we see over here that someone came up with this for ammonia production, that if you mix these two catalysts, if you mix cobalt and iron, you might just land up somewhere in between. It's a simple interpolation, right? When two endpoints meet, like a midpoint theorem or something like that, you reach the middle. They tested cobalt and molybdenum and they saw that yes, the TOF is certainly increasing, and by designing a bimetallic alloy, you can actually try to enhance the turnover and come up with a better catalyst design for a particular system. Now, all of these is a single descriptor. We are trying to analyze the turnovers or the production rates with the help of a single descriptor over here. Now, let me just give you a glimpse of what all reaction steps are there and everything. For instance, this was the reaction that I just listed out. Now, this is my ethanol, right? Ethanol can lose the alpha hydrogen and form the species. It can lose the beta hydrogen and form the species. There can be CO bond scission, there can be CC bond scission, and there are a plethora of reactions which may occur. When we made the model for this reaction, there were actually a total of 101 elementary reactions taking place. And these are the initial dissociation steps that are happening. Now in this model, we had to list out the differential equation for every elementary step, right? Elementary step is that step wherein a single bond is broken or a single bond is made, right? So we had to enlist that, and then we had to have energies for every single step. So like, for instance, I had to have energy of this one, I had to have energy of this species also, and then also the energy of the transition state, which is formed when you convert ethanol to, let's say, the species, right? So all of that was calculated from DFT calculations, or there was previous literature available for it. And we just got that from the literature. So this represents the reactions which we did not solve. We used CatMap, which uses multi-dimensional Newton's root finding method from the Python MPMath library. And please don't get overwhelmed by these equations because this is not what we solve. We just make the model, we just enlist all the possible reaction steps. Then obviously the programming software does the solving and we don't sit down and solve it physically, but all of it is solved for a steady state approximation. And these are the two important relationships which have been implemented in these solutions. The first one is adsorption energy scaling, and the second one is transition state scaling. So adsorption energy scaling basically tells us that energy of any adsorbate scales with the energy of descriptor. Now, through the passage of all the work that I've done, mostly I've been dealing with hydrocarbons, and the two descriptors that we've used is the carbon binding energy and the oxygen binding energy. Hydrocarbons also have hydrogen, but hydrogen is so small that its adsorption does not compete with any other molecule or any other atom. Therefore, that is not a good choice for a descriptor. Now, for instance, over here, we've used carbon and oxygen binding energies as our descriptors. Those are basically So for instance, this is my ethanol, and I represent the energy of ethanol with respect to the energy of carbon and energy of oxygen on different catalyst surface. Now, for us to run our model, it is essential that we have the descriptor energies, which is carbon and oxygen binding energies on all the catalyst surfaces that we're exploring. And for the rest of the catalysts, we should have at least, there should be at least 3 catalysts, for we should have all the data, for the entire reaction scheme that we are evaluating, every transition state and every adsorbate species. We should have those energetics calculated from density functional theory calculations. Only then can we execute this kinetic modeling. So then transition state scaling is also there. So it says that every transition state scales with a dissociated state, and the dissociated state will eventually scale with the descriptor. So we can represent the energy of everything with respect to the descriptor. And finding this descriptor-based analysis, which was introduced when the CatMap paper came, this was basically developed in SunCat, California. And my postdoctoral supervisor, basically at IIT Delhi, Dr. Tuheen, he was the one who helped me learn all of this. So this is basically descriptor-based analysis, and we see that it greatly reduces the dimensionality of the problem, because just with respect to carbon and oxygen binding energy, I can predict which catalyst is the best. The maxima that we saw over here, this is a 1D maxima, right? It's a single descriptor. It basically corresponds to this orange region over here, and I'll be delving more into it right now. So this was ab initio microkinetic modeling, which I did over the course of my PhD, and beyond that I've been doing. We use simple model molecules, and then we do descriptor-based activity plots, we do selectivity control and coverage analysis, we do degree of rate control, then we get insights into different reaction pathways, we compare with experiments and see which catalyst will work, which won't, and then we come up with design of bimetallic alloys based on selective activation of different bonds for catalytic conversions or catalytic transformations of alcohols and alkanes. All of this I have done so far, and I'm still doing. So the first reaction I'll talk about over here is water gas shift catalysis. One of my internship students, Zakaria, has worked on it. He's finished this problem just the last month and submitted his paper. So the reaction goes on like this. Carbon dioxide and water reacts to form carbon monoxide, and water reacts to form carbon dioxide and hydrogen. So it is actually much simpler than the reaction pathways I showed before. So the ones in red are the reactants. So CO and H2 are my reactants, and CO2 and H2 are my products which are being formed, and they can be formed by these different reactions which are occurring. I think it's maximum 30 reactions or 20 which are occurring over here. And then Zakaria built this model at 573 Kelvin. Now, when we construct a microkinetic model, we have to appreciate the fact that a catalyst has different sites on it. A catalyst has a 111 site or a 211 site or a 100 site. So you can see over here, this catalyst, that structure that I've shown, there are different kinds of facets to it, right? You may have studied that. So terrace sites are the 111 sites. These are the flatter ones, and step sites are the 211 sites. Now there are more under-coordinated sites at these 211, which means that 211 sites will have a higher propensity to bond with anything, So it will act as a better catalyst as compared to 111 or 100. Therefore, we constructed the model at 211 sites. Now, in water gas shift catalysis, we went through the literature and we saw that there are basically 2 competing pathways. There is the carboxyl pathway and the formate pathway. This is carboxyl and this is formate, and we wanted to understand which is the dominating pathway, and we constructed the model for it, generated the energetics for it, and we saw that it's the carboxyl pathway which shows a higher turnover. You can see over here, this orange region lies somewhere around here, whereas the blue and the green region are far low. So the turnovers for the formate pathway are far low, and we can easily say that it's the carboxyl pathway which is the dominant way to move ahead. So then we analyzed the production of hydrogen, and we saw, oh wow, copper lies closest to the top of the maxima. But the rest of the transition metal catalysts are showing lower production of hydrogen. And we wanted to analyze why that happens. So we observed the coverages of CO, and we see over here platinum, palladium, and all of these show very high coverage of CO, which means that the catalyst surface is being poisoned by carbon monoxide, which is something we have to evade in order to come up with a better catalyst design. on carbon dioxide to poison the surface. If carbon monoxide is sitting on the catalyst surface, what is happening is that it's leaving no space for the reaction to occur. Therefore, no hydrogen is being formed. So we then did some degree of rate control analysis. To put it in simple words, degree of rate control analysis tells us which intermediate, which adsorbate, or which transition state has a higher impact, is more rate determining, let's say, is more rate controlling. And if we have a positive rate control, it means that if you increase the rate constant for that reaction, or if you basically make that more stable, the reaction, the product formation rates will increase. So if you increase the rate constant, it increases the net rate reaction. Whereas if you have a negative degree of rate control, it means that if you increase the rate constant of that reaction, the rate of reaction, the rate of overall reaction decreases. Because we do appreciate, right? It's not a single reaction that is happening. It's not this reaction which is occurring over here. It's all of these elementary reactions taking place for you to see this larger reaction to take place, right? So we did the degree of rate control analysis, and we saw that it was only CO, which is the carbon monoxide adsorbed on the surface, which had a pretty negative degree of rate control on the production of hydrogen. So if you make this CO more stable, it just means that hydrogen won't be forming. So how do we evade that? How do we actually increase the degree of rate control, make it more positive so that CO does not have any impact on hydrogen? So we observed firstly that it was coverages of CO which led to such negative degree of rate control. And then we saw that alloying could potentially be a way forward. And we did rigorous testing of these alloys computationally. So we see over here that as you alloy these catalysts, you move from, this is basically the CO coverage, you move from the red region to the blue region. And you see how the coverages are decreasing as you are doing alloying. And as you do alloying, the coverages decrease, the degree of rate control becomes 0, right? Green is like 0.4. So it is now becoming more positive, and consequently, your turnovers are increasing. So alloying can help come up with novel catalyst design, which we suggested from this study. So these are the catalysts which we suggested, which we did from our modeling. These are the ones which have already been tested experimentally. So the novel alloy formulations, one second. So the novel alloy formations, how do I?
What do you want
I
to
just
know?
want to hide this tab over here so that I can show what the novel alloys are. Yes, thank you. So the novel alloy formulations which we came up with were these. And any experimentalist can test it and then can, just see if they work out well. And they surely will, because it's backed with all the ab initio microkinetic modeling. So another implementation was dehydrogenation of alcohols. Now, alcohols obtained from biomass or fossil fuels, if you do dehydrogenation, we can form these value-added chemicals and fuel additives. Now, this can be done by oxidative dehydrogenation, but the problem with oxygen is that it's an unsafe process because of oxygen. The oxygen has a higher propensity to deactivate the catalyst surface, and then the selectivity would get lowered down because of oxygen. So a way forward could be non-oxidative dehydrogenation. Now, not using oxygen enables the process to be safe. The catalyst will be stable. The selectivity will be higher because there's no oxygen, so there won't be any side product formation, and then there'll be production of hydrogen. And we ran this microkinetic model, basically MKM, on transition metal catalyst surfaces. So these are the decomposition routes which we evaluated. Now, the non-oxidative dehydrogenation of this ethanol we took as a model molecule to understand these reactions at large. So if it undergoes NODH, which is the non-oxidative dehydrogenation, we have the production of acetaldehyde. But it can also undergo dehydration, which will form ethylene. So this is what we want, right? We want catalysts which will form acetaldehyde and not ethylene, because that is the goal of non-oxidative dehydrogenation, the production of these value-added chemicals, fuel additives, so on and so forth. So 103 elementary reaction steps. So the equations for 103 elementary reaction steps were solved. And again, the model was constructed for step sites because they're more active. Over here, we can see that as the catalyst surfaces, as the catalyst size is being increased, the turnover is decreasing. what happens is that with the decrease in platinum particle size, the number of under-coordinated sites increase, and that is why the turnover is increasing. That is why we constructed the model on 2-on-1 sites. The results which we observed. Platinum is the best catalyst for this, most active. It lies at the top of the volcano curve for the production of acetaldehyde. And it's just gold and silver which are forming some levels of ethene or ethylene. So this corroborated with previous studies, wherein, for instance, this is NODH of 2-octanol. They also observed platinum, the rates to be highest on platinum. This one is NODH coupling of 1-octanol, and they also observed the yield to be highest on platinum. So this corroborated well with what we had done. We also observed platinum to be the most active catalyst. Then we started unraveling the coverages of different species, and this is what we observed. What is interesting is that copper is the only only active transition metal catalyst which is showing the coverage of this ethoxy species. The rest of these are showing coverages of CH3CO, which meant that copper is not a good dehydrogenating element or a metal or a catalyst, whereas platinum, palladium, rhodium, nickel, they're all dehydrogenating too much. Now we had to tune in that high dehydrogenating capacity of these transition metal catalysts. And again, alloying is the way forward, right? So this reaction route was the mechanistic focus, CH3CO, which was inhibiting the surface of copper, and CH3CO was inhibiting the surface of the rest of the active transition metal catalysts. So we alloyed copper with nickel, rhodium, and platinum. And what we see over here is that on alloying, we see that platinum moves this way. All of them are moving towards the edge of the volcano plot, right? Towards the edge of this red region, signifying the decrease in coverages and consequently the increase in the turnover. So just upon alloying copper with nickel, rhodium, platinum, and palladium, you see that there is a order of magnitude increase in the production of acetaldehyde. So this was again corroborated with previous studies. This was a study done by Wang et al., wherein they used platinum copper single atom alloys, and they saw that there was a 6-fold increase in the activity of copper 111 once you made a platinum copper single atom alloy for it. Then similar observations were made for single atom alloys of nickel copper, and they saw that activation barrier reduced from 70 kilojoules per mole on copper to just 47 kilojoules per mole on nickel copper. One other study on dilute nickel copper alloys corroborated the suggestion that we had made. This was not on single atom alloy, it was a dilute nickel copper alloy. The experimental study on ethanol NODH over bimetallic nickel copper measured a lower activation barrier of 45 kilojoules per mole than that of copper catalyst, which was observed to be 70 kilojoules per mole. So next we tried to see what happens to the other metals which are dehydrogenating too much. And we see over here, we chose nickel for our study. It's forming a lot of CH3CO, so we have to curtail that. So we thought, how about alloying nickel with tin? So we see that once nickel is alloyed with tin, the dehydrogenation barrier, basically the barrier, the transition state for this reaction, you see that the barrier is increasing. The dehydrogenation barriers increase when you alloy nickel with tin. So the proposition was when you alloy nickel with something which has a lower propensity to dehydrogenate, we will be able to tune the overall dehydrogenation capacity of the alloy. And that is what happened. This is CH3CO. Once you alloy that with nickel, this is nickel tin. So it shows no coverage of CH3CO anymore. And then it shows a high production rate of acetaldehyde. It lands straight at the top of the volcano curve. I think I've repeated that, yeah. So after this study, we augmented our study for the in silico high throughput screening with machine learning. So far what we did in computational catalysis was we were using DFT and we were using microkinetic modeling. So all of it we were getting from density functional theory calculations. And that is computationally very intensive, right? So we thought, how about using machine learning and just circumventing that as well? So we implemented this machine learning for this NODH itself, and I'll just be showing you the results. This was done as a part of my PhD dissertation. So I did the MChem part. This is not what I did myself, but it's very interesting to see that we were using descriptors, right? Carbon and oxygen binding energy. And we thought, why not use machine learning to get us to those descriptors? And we used various machine learning algorithms, and we saw that the gradient boosting algorithm was showing us the lowest error of 0.31 electron volts. And these were the different features which we used for the bimetallic alloys, okay? So this is the A or the B metal. And we saw that between ML and DFT, the predictions are pretty close. There is not a difference of more than 0.3 electron volt in there. In the descriptor energies. And we also observe over here, you see the turnovers. The turnovers are pretty much in the same range. There's only a difference of 1 order of magnitude, which means that ML can potentially be used to predict the descriptor energies of large number of alloys, by means of which we can accelerate the process of catalyst discovery at a much lower computational cost, because we do not have to do DFT again. So this was the summary of the non-oxidative dehydrogenation reaction which we did. These were the novel alloy formulations we came up with in this entire study. Now I'll be talking about the applications of ab initio microkinetic modeling at large. So you can come up with enhanced catalytic systems for cleaner operations, utility chemicals from sources other than fossils. You can look at ways to enhance the fuel efficiency, on combating climate change by reducing carbon footprint and global warming. We can also look at different fuels and fuel additives from biomass. We can also look at creating better systems for water purifications, solutions for carbon dioxide capture by amines, alternate energy sources. So all of this can be captured if we are implementing these ab initio microkinetic modeling and simulations. Now, with all of the research that I've done in my PhD and also after that, I would like to talk about a little bit about research with all of you. So how to approach research. Now, you may already be into research, or you may be looking forward to get into research. So this is how you should be going ahead. Firstly, you identify the broad research area. Then you try to understand the phenomena, right? What is happening in your research? You have to try to understand the concepts behind it. And I would really like to highlight this part. You cannot just let go of it. You have to understand the details of it. You have to appreciate what's happening. And then you have to look on to finding the research question that you have. You have to identify the gaps in literature, or you just have to come up with what you want to do. Then you come up with a hypothesis and you test your hypothesis, right? This is the general protocol in most of the research applications that you have. Now, this might sound a little out of context, but let's take a look at these sunsets. You know, setting sun, we see it almost every day if the sun is clear. So imagine, I want you just to close your eyes for a minute. It's sunset over here almost. So imagine the setting sun, or just think about it. When you look at a setting sun in real time, are you looking at the past, the present, or the future? So I want you all to think in your own places that what are you looking at? Well, it might seem to the most of us that we are looking at present. But we do realize that light takes some time to come from sun to us. Yeah, 8 minutes, as we all studied in school. So what we actually look at is always the past, because light takes some time to reflect, right? And also light takes some time to travel from the sun to us. So that the sunset I'm seeing, or that a sunset I see in real time, is actually the past that I'm seeing. So these things around us, the nature around us, should make us curious. And I want to tell you all that we have to keep our curiosity about the world alive, and we have to work consistently to make it thrive. When we understand science and when we start to look at science in that way, it will become more appealing to us. We will be able to unravel more mysteries of science, and we will feel like a scientist, even if it's not about degrees and accolades and everything. It's about the mindset, you know. So the beauty of science lies in unraveling the workings of the universe, and one, when finally understands, the simplicity of the answer is what leaves us in awe, right? Like, just like it's mesmerizing to know that, okay, the sunset I'm seeing is 8 minutes in past, and everything else is basically a fraction of past. And what is the most amazing thing is that light that reflects from everywhere is somewhere in the universe, right? And if someone puts a projector in the universe, they can just play the movie of what we all do or have done, right? So About research, this is the first thing. You have to be curious, you have to know, you have to want to explore, you want to understand things. I know it is easy to say when you are done with things, I know that, but from my experience, I want to tell you all that once you are in the process, remember to appreciate the science of it. Don't be huddled by or by the hustle of this world. Don't just get carried away with that. And I know there are pressures and there are deadlines. You have to submit a paper, you have to submit your dissertation, you have to give a report to your funding agency and everything. But in the middle of it, if you try to keep your curiosity alive, believe me, your work will be 100% better than what it would be without that curiosity. Now, once you are into research, writing has to be your hobby, maybe. You have to write down your ideas, your results, and everything that happens in between. You should be reading a lot. Reading in general, I think, is a very good quality to imbibe. If you, I think everyone should try to read as many books as possible. But if you are a slow reader or if there are too many things on the table, you should always keep a book in your bag, by your side, everywhere. And, not waste time maybe on the internet or anything, because one should try to read as much as we can, because it broadens our horizon at many levels. So that is general reading, but for research, you should be reading papers. You should be using AI tools to find the most important groups working in your area. Now, that wasn't possible some years back, but you can use AI to enhance your productivity and not, um, kill your mental activity basically. So and also whatever you're reading, you should compile it in a presentation so you can look back, okay, fine, that day. Otherwise you just forget. You read papers and you forget what's happening, but once you have it in a presentation, you will know where to go when something strikes, when an idea strikes. You should be downloading all your references in any referencing tool. I use Mendeley. To get an overview of paper, for instance, I'm reading a paper, I should be reading the abstract and the conclusion for it. I believe that is enough. But if I have to implement their methodologies, I should be very thorough with that section. Now, as experimentalist, I did some experiments also, which I'll be talking about shortly. So once you do experiments, what happens is that you just go into that, that vibe of experimentation and you forget to write down your results, analyze your results. You're just doing millions of experiments without analyzing your results. And believe me, it does not hold any meaning if you don't analyze your results. When you start to write down your result, you appreciate, you understand galtiyan kahan ho rahi hai, and you understand how to do further experimentation. So that will gives you basically a pathway once you write down your research. And I believe not just researcher, every student of knowledge or every person should have a practical timeline to stick to, and also a doable everyday to-do list. So that gives you basically, this is, I have to get this done. You are focused, right? Now, once you start writing your research, I believe you should make a skeleton first, which gives you an outline. Let's say in introduction, I have to talk about 10 things. I have to talk about global warming, catalyst, microkinetic modeling. So I just write those down. Then I can easily elaborate on those. And for writing, use Grammarly for all the grammar mistakes that you might make or similar tools. Now there are so many tools out there. I don't have a clue, but I think you should go out and check those out and use them. Use them to your advantage, but don't give your brains to it, okay? You should use it to augment your brain. Next, and the most important one, in-depth discussion with supervisors and peers. This is so, so important because once you're into research, if you're not discussing, firstly, you have to be curious, then you have to discuss, because once you discuss, new ideas come in and then new ideas take place and things bloom in your mind, believe me. So you should be discussing. Scientific discussions should be happening in your research. Now, research, the predicament is, what if the ideas do not turn out as we thought, which happens very often in research. Research is but a sum total of these failures that paves the way towards the answer. So every misstep, every miscalculation, every experiment gone wrong is actually an answer in itself, guiding you forward, fulfilling as a whole, even the failures, and then one appreciates it mostly at the end of the tunnel. At the end of the journey, when you see everything, you are able to appreciate it. But as a person who just came out of this tunnel, I'm telling you, appreciate it even through the journey. I'll just tell you a few stories from my PhD. So when I started my PhD under Professor Heather, I was given a task, an experimental task to do electrodialysis, purification of biomass-derived platform molecules. The problem was these platform molecules have some amino acidic impurity, and I had to remove that using electrodialysis. Now, electrodialysis means that there are these membranes which allow either cations or anions to pass through, and there is an external electric potential that you apply. And we have these amino acidic impurities. What we did was that we thought of operating it at the isoelectric point of the amino acid. Let's say I have methionine. So operating at the isoelectric point, it means methionine will be immobile. The Zwitter ion will have the same level of positive as well as negative charge. So it will not move, but the platform molecule will move. So this anion will pass through the anion exchange membrane and move towards the anode. So that is the reaction happening. And I did this experiment. Now, as I told you already, my PhD was not a full-time PhD, right? I had to teach. So I did this experiment when I was at IIT Delhi for the first year, and then I did it in months. Then I had a BTech group who did a wonderful job at that experiment. But I wasn't able to give complete time to it because obviously because of the mode of my doctorate. And I had to train other students at it and I had to give up this problem. So at that point of time, it might have seemed to me that, oh my God, everything is changing. But I tell you again, flexibility and fluidity is very important. So I trained other students on it and they helped complete it. Otherwise, for this thing, I had done lots of experiments, catalytic experiments also and everything. Because what happens was that amino acids have that sulfur and they inhibit the catalyst surface. That's why we wanted to take them out. So eventually, I contributed a lot to it, but it did not end up being a part of my PhD, but we got a patent in it. So my hard work did not go to waste, and hard work never goes to waste. So even if I would not have gotten a patent in it, getting a patent does not mean that does not actually is not like the story has ended or anything of that sort. Sometimes the exposure that we gain from it and the process of going back and forth, the resilience that we build, the persistence that is built, and the flexibility that is built is more of a award than any other thing, you know. So it's a book I read, The Boy, the Mole, the Fox, and the Horse, and it says this quotation. It has this quote: "One of your greatest freedoms is how we react to things." So our experiments fail, and if we lose hope at the failure of our experiments or at our hypothesis, that's the wrong way to deal with it. We have to make sure that we deal with it with perseverance. You know, experiments don't work out the way we want. We can tune in other factors and see how to make them work. And all of research and all of life, basically, what matters is that we give ourselves the gift of time and patience to work through these hurdles. And that can help us become better people, better researchers, better students. Now, addressing failures. We fail, right? We all fail. And I forgot to mention, so failures, obstacles, let's say in my my PhD started in January 2016 and I had to work on my dissertation. So in January 2019, I gave my synopsis, and after that, we get 9 months to submit the thesis, but I could not submit the thesis in time, and I got an extension for a couple of months. But over here at NIT and over here at NIT Srinagar, they wanted me retained for some work, and it was getting very, very difficult for me to go to IIT Delhi because I wanted some secluded time to work on my thesis, to work on the compilation. So with a lot of effort, I finally was able to go to IIT Delhi, and then I finished up in a couple of months. My supervisor worked very hard with me, obviously, and then I was able to submit my thesis. That again was a very huge obstacle in my research path, apart from the fact that it was a part-time research. But then I was able to defend my thesis in July 2020, which was a great thing, which would not have been possible without my supervisor's efforts, with the department here at NIT Srinagar, and obviously my family. So when we have these failures, these obstacles, I want you to look at these 9 dots, and I'll just come up with an answer from these 9 dots. So think about how can you connect, or you can take out a paper if you can, if possible, if you have a paper at hand. You have to connect these 9 dots in the square using 4 straight lines without lifting your pen from the paper. Now, I'm not sure if time is on my side, but many times when we solve this problem, what restricts us is this square. Connect the 9 dots in a square, right? And let me just show you the solution anyway. This is the solution. This was the square initially, but only when you go out of that square, you get the solution. So you have to make sure that you think out of the box. You don't have to restrict yourself to that square. You have to connect the dots in that square, but doesn't mean you have to be in that square. You can go out of the square, right? So the simplicity of this answer is so baffling, and it makes it so beautiful that whenever you have obstacles, we all face obstacles. We just have to be calm, composed, and we have to come out of the box and address the solutions. Now, some common problems that I see with students and how we should be going about it. I see social media as a huge, huge distraction for everyone, basically. So I think that should be curtailed. Peer pressure. It's like everyone wants to jump into the same pool. That is not possible. We all have our own individuality. We all have our own strengths, own weaknesses. And based on that, we should be designing our careers or designing our goals. It cannot be the same as the person sitting next to me. And then there is expectation of overnight results in research. That doesn't happen. Studying solely for grades, as I emphasized a lot of times in my presentation, I think it's the understanding which is the joy of studies. So one should really focus on understanding things, and other things will follow through. So my supervisor used to tell me to pick up 4 problems at the same time, because if I pick up 4 problems, I know at least 2 of them I can bring to completion. And he used to say al haraka fil baraka, which means there is, blessing in action. So you have to keep moving. It may not always be that all the movements give you result, but if you're static, nothing is going to move for you. So lack of proficiency in the use of various tools, lack of proper counseling, that is there, that has been there since I was a student also, but certainly it has gotten better. But what a student of knowledge must try to imbibe, what they should pursue for: persistence, resilience, hard work, thoughtfulness, flexibility. I think flexibility is important. Hard work is also important. You should always try to upskill yourself. You should never be stagnant. So you should not waste time, basically. If you have time at hand, you should be using that time to upskill yourself, as the world is getting more and more competitive now. You should be informed of the current trends in the research as well as the local problems that can be addressed with research. You should be having fruitful discussion with your teachers and peers, which I emphasized before. And you should not expect the table to be ready for you. You have to work hard on getting the table ready for yourself. You should be looking out for opportunities. This is very important. If you want to do anything, basically, you should be looking out for opportunities rigorously. You should do thorough research for internship opportunities within country and abroad too. You should be visiting the research internship websites regularly. And then there are research internship opportunities at IIC, IIT. They have a summer internship program. You should be applying for that. These are different. This is the DAT internship program, UNICEF internships, Erasmus Plus, IUSSTF, which is in US. These are all the internship programs abroad, which can give us a good exposure. Then you can use AI tools to give you the perfect opportunity that you may be looking for. But you have to be flexible here also, because you have to look for remote internship opportunities as well, in case you don't find a physical one. Then you have the interview, you go ahead with the interview, and you should be aware of your strengths as well as shortcomings while you do your interview. Now, when you go ahead for internships, it's important that you write an amazing CV for yourself, wherein you're listing out your strength, but you're not being too boastful about it. You have to make sure that it's thorough and you're mentioning all your achievements. You might see that it's a very small achievement, but you should put it there. Then you also should be writing a meaningful statement of purpose that will help you, because many internships ask for it. And even if you have it in front of you, you will know your strengths, your weaknesses, basically self-analysis. It's very important because it will help you understand yourself. And that is the first step to going anywhere, right? And then you have to network. You have to send emails. You have to send emails to your alumni, batchmates, professors, family, friends to get you an internship or a job or anything. But sometimes you don't find any opportunity. So you have to learn how you can create one. And for that, reaching out to people is very important for you to create your own opportunity. I have a couple of slides on some resumes. Now look at this resume over here. These have been submitted by my students. So over here, I feel that this resume is too brief. The scores haven't been mentioned over here. The achievements haven't been highlighted or explained further. Now, this was a little better resume. The scores of previous academic qualifications mentioned, the achievements highlighted, and the extracurricular activities have also been highlighted over here, we can see. Now, finally, this resume, the person has in detail mentioned everything and what they did over there. This is pretty impressive in that sense, because someone reading it would see all the honors and the awards and everything. and the scores that they got. Sometimes the scores are not that good, and you don't want to put them in, but most of the times that may not be the case. And even if it is the case, you can skip that. But you should be working on building a good CV. Now, I don't mean to say that you do good things for the CV. You do things, but you make sure that you write that in your CV as well for you to land up in better opportunities. Now, some more opportunities. These are all for women. I can be sending out these if you want. So this is mostly for women in STEM in India. All of these are there, and women do face some obstacles. And for that, there are special schemes, and we should be tapping into those schemes and making sure that we do not let those go to waste. Now, lastly, I want to talk about giving it back to the community. So, with the help of the research that I'm doing here at Catalysis Laboratory, envision to use it basically for Dal Lake purification. I want to use the aqueous phase reforming of waste from Dal Lake and convert it to hydrogen. That's one of the projects I want to work on, and I'm currently delving into it. Then I want to work on development of materials for enhanced purification of water bodies. I want to work on the conversion of waste from Dal Lake into biogas. And lastly, fabrication of advanced materials from locally procured fruit and plant waste. And I think giving back to the community is important in the sense that they are the ones who groom you, right? So basically, as a teacher, I think you do give back to the community and you do give back to the students. And if you invest in the student, it is like a form of giving back. But in terms of research, these are the SDGs I want to focus on: clean water and sanitation, affordable and clean energy, responsible consumption and production, by working on these problems that have been listed over here. With the work that I did, I want to thank my supervisor who helped me, Professor Haider from IIT Delhi, and REC Lab at IIT Delhi, then Catalysis Lab over here at IIT Srinagar, and all my students. From the day one, I have had wonderful students who have been teaching me. Being a teacher has been a very, very emancipating journey for me. I have learned so much more from them, and it's a beautiful thing. So I think giving back has that biggest thing, because it is not the students gave me, and it's not me giving back to the community. And I want to thank Pune Knowledge Cluster for giving me this opportunity to talk over here. Thank you so much, everyone. Thank you for listening.
Well, thank you, Fatima. It was a lovely talk, and got a good mix of both the heavy science and also very good of you to mention all the mentoring points that you had mentioned towards the end. I think the whole ensemble would be really nice for somebody to even go over and flip through these slides. So if somebody requests, I would probably be asking you for these slides to share with the students, parts of it, like you mentioned, the women program and everything at the end.
Yeah, I'll be sending those parts to you.
They are very useful. Okay. So we have some time to take a few questions with you. I'd like to go over a few parts of what you mentioned in your talk a little bit more deeply, just to understand
Yeah,
more
sure.
more about you, basically. And I think I'll open the session for students to take the technical questions, which will be more direct about what you do and how you do this experiment. So I wanted to first understand, coming from a heavy research background and then also getting inducted into teaching fairly early, I'm sure you like both of them, but do you have a preference, teaching over research?
It depends maybe on the course that I'm teaching. If the course is interesting, appealing to me, then it would be teaching over research.
But you still enjoy teaching overall more than doing research? Would it be
Yeah,
like that?
I guess so. Yeah.
Because research is seldom very, like I said, rewarding.
Yeah.
The thing that
Teaching is very rewarding.
you feel
It
nice.
is. Yeah.
So, who would be your role model? If you have any, would you like to let us know?
My parents.
Okay.
Yeah. So I've looked at them. They're very hardworking, very disciplined, and that's what I want to embody. Even as a parent, I want to become like them. And my supervisor has been a professional mentor in my professional research journey. But overall, it's my parents, I think. Yeah.
And for a very successful career where you are getting, these awards that we see, and at the same time your teaching is going on, and you're also getting into your dissertation, which is, of course, you have to stagger it, like we understood from your talk. But who would be the catalyst in your life who made
My
all these
supervisor.
things?
My supervisor.
Okay.
For my research part, it has been solely my supervisor who's been pushing me to work. And because obviously, working in this mode wherein I have to do multiple things, it was my supervisor who helped me, prioritize, let's say. So, helped me, pushed me to apply for different awards and do all those things. It was my supervisor. But obviously, to manage between all these things, it was my parents and my husband's support. I mean, I got married towards the end of my PhD. So, but still, the support from family. But the catalyst would be Professor Heather.
Okay. So I had a question from here that it's coming from an interpersonal relationship. These days, it's very difficult for students to develop that, I would say, chemistry or that kind of an understanding, or, a brainwave with their guides. Because would you be able to help us understand what would be a very healthy way of keeping this rapport with your guide so that he can assist you and be the catalyst for you when your career needs it most, and you're not shy? Because I think women on the whole are very shy, or they are held back. Or how do we do it? I mean, would you be able to
Uh,
shed some light on this?
I think it also depends on the supervisor, right? I mean, it's a two-way.
Two-way, yes.
Yeah. So it certainly does depend upon the supervisor, but I think students should be more proactive. Mostly it's like if you're working hard, if you work on something, you have to make sure that you show it to your supervisor for it once, right? Because if you're not, I don't have that exact word for it. I don't remember it, but it's like you have to keep coming to your supervisor to show him that, okay, I did this, I did this. I understand supervisors are very busy and they might not have the time to, but if you come 10 times, I'm sure one time he's going to take a look at it. I don't mean to say, I don't mean to demonize anyone, but what I mean to say is that I know everyone has a lot on their plate, but it's like we have, as a student or as anybody, we have to keep trying. The moment we stop trying is, which means we give up basically. And then we cannot put the blame on the other end. So we have to keep trying. And as a student, it's my research area, right? So I have to keep trying. I have to see different ways to solve it. And then my uh, supervisor has to be that catalyst. And if sometimes it may not always be the case, right? The supervisor cannot always be the catalyst of the student. Sometimes the supervisor is very busy with his work and he may not have the time for his research, the addressing all the research problems, right? So at that point of time, the student has to take that responsibility for themselves. He or she, they have to, basically she has to network with the lab mates, network with other labs. You have to find people who will make you grow, not people who bring you down, basically.
Because I think the students are at this stage right now where studying in the classroom, where you sit and keep quiet and just study, is
Mm.
very different from research, where you are proactive and you need
Yeah.
to go out and actually research, work on your own as
Mm.
much as with others, as in a network, a way
Yes.
of
Yes.
exchange. Another thing I wanted to ask is, in research, often girls are given to understand that if you discuss your work, it will get scooped. Now this kind of, it's very difficult to actually explain them how discussion, could you shed some light on how to get?
Yeah. I would say you just should discuss your work in your with your own lab mates, or broadly, like you don't have, let's say I'm working on a catalyst and it's microkinetic modeling of some reaction. Now I can discuss microkinetic modeling with people around because everyone knows what microkinetic modeling is, but I would rather not talk about the reaction that I am working on and the specifics of that reaction. So that is, I think, and I mean, you people will learn that, students will learn that with experience. We all make those mistakes and those, those sometimes something slips out of the mouth or something. But discussions mostly with supervisor and peers, I just if they have a lab where they're working at and there are other students, they should be discussing it because it creates a very scientific atmosphere around. And when there is a scientific atmosphere around, everyone wants to think more, everyone wants to be a little more than they really are, uh, like it is like it might just create a sort of peer pressure to be more brainy, or I don't know, to be more thoughtful. Now, I do not mean to say that there should be peer pressure, but there should be an environment which allows science to bloom in their minds.
Exactly. They should have a habit of having a healthy debate at least,
Yes.
keeping those details not so obvious, which might kind of lead to these things. But it should no way stop them from presenting posters. It should not stop them from having a debate.
Yeah.
Okay. So you did the trainee teacher
Yeah.
scheme, which was very early in your career.
Yeah, it was very
How was that responsible in shaping the excellent educator that you are now? Did it actually, or were you inherently like very nice at teaching because you said your
I
mother was a
wasn't.
very good teacher?
No, I wasn't. I still think I'm an impatient teacher, but that was my 2017. It was my first time I was teaching the course, and I think my students will have a lot to say about it. I was very strict, but I was working hard on teaching them. So I was working hard on learning myself, and that I think came out when I was giving those lectures. I learned a lot myself to become the teacher. Now, I won't say I taught all the courses with that same vigor and everything, because it was the first time I was teaching. But uh, teaching did not come naturally. I had to learn it. But then now I really love, if I have a good class, a class which responds, which has there should be a two-way conversation. I really love teaching those people. Now, even if there are 10 students in my class who I know are listening and are responding back and are thinking, that makes me so happy. And then, it is an exciting thing. It is again the same thing, the joy of understanding that I highlighted all through. It really, I think, boils down to that only. So
I
then you
also
have to
noticed.
communicate that joy, and you have to, basically make the other person appreciate the beauty of whatever process you are trying to study.
I have noticed that most successful people in science uh, often say that their teachers, they had good teachers, and so they are where they are because they loved the science, because the teachers were very inspiring. Do you think that's really true?
I do think so. I had wonderful teachers. I used to have random questions, and I had a physics teacher in my school, uh, Manzoor sir, and I used to go to him with the sunset problem that I just said. That is the first time I took it to him. I was like, uh, "This is so baffling that the light that reaches us took 8 minutes and it's passed." And then he's the one who told me, "You know what, Fatima? If you put a projector out there, all the light will go out in the universe, and we can just see everything that happened anytime in the universe, because that light is somewhere in the universe." So my teachers were amazing in school, and then my friends were amazing in the sense that I had a group of people around me who were always talking about this understanding things and everything in discussions. I think that really uh, was the thing. And then my students, now, I think it was last year, I got an email from my student, which was the first batch that I had taught in 2017. And he wrote to the, I don't remember clearly, but it was something like this: to the teacher who knows all the magic tricks of making things simple, kuch aisa hi likha tha usne. And I was so happy. I was so happy. It was just one email, but that made that's enough. Small things that make a lot of difference.
So I think I have a few questions that I think I can see in the chat, and they are, some of them are very interesting, and I would like to pick one and ask you, does your PhD degree affect your future career? From which institute you get your degree, does it matter or it doesn't?
It does and it doesn't. It wouldn't if the quality of work that you're doing is excellent. It will not matter. If you work hard on it, no matter where we have people. I mean, let me just compare. Like IIT Delhi, obviously they will land up in better opportunities than IIT Srinagar. But we have people over here who landed up in wonderful postdoc opportunities in US, in UK, based on the kind of research they did. I think the your pursuit matters the most. You should be working hard. You should be working diligently. You should make sure that whatever, the quality of the work should be good. And then you have to reach out to people. That is very important. You have to keep sending emails and everything, and then opportunities do pop up.
Fatima, I noticed that you were saying you shifted to ML, machine learning. Are you somebody who has been doing machine learning, or did you learn it as a
No, no,
new?
no. I said it over there. Machine learning part was done by someone else in the lab. I was doing the MKM part. But yes, I am. I have students who are working on machine learning as well.
So if we all, like, let's say all of us are old and we go into the next few years from now where machine learning and AI would be predominantly utilized in every laboratory, how do you see yourself as a teacher coping up with it? What would it be like for you? Would you learn it? Would you, I mean,
I always think I should be learning it. I haven't had the time to, but I think I will be learning it myself. My students implement it. I know broadly what it is, but I'm not able to do it myself. But yeah, I would love to learn it.
so you mean even as a teacher in science, you don't stop learning till the end of time?
No, no, no. You don't stop learning.
That's
No.
okay.
And
Thank
more
you.
so as a researcher. As a researcher, you absolutely don't because you're just, which is good also. I mean, there should be a balance. It should not be complete research also because teaching is amazing, but a little bit research should be there to keep your mind working.
So, what do you think is more? Where do you think the learning and the updation is more, as a teacher and as an educator, or as an just as a researcher? Like, if you are doing research, you will be updating yourself more, or is it as a teacher because you come across the younger generation and so you have to update yourself more? Like, like a phone has updates and a computer has updates. What is the, you know,
I think personally,
pro-
as a researcher, you have to update more because what I'm
because
teaching, it's like it will remain pretty much the same for a few years, then it might change. So, but teaching teaches you different things. Like the same thing I might have understood differently when it was the first time I taught something. In 2017, I taught the mass transfer course. I understood it at some level. Now, the fifth time I did not teach it 5 times, but let's say the third time I taught it, my understanding was next level. So the more you study something, the deeper your understanding gets on that subject.
I'm also asking this because most women have a time in their career when they need to take a break.
Mm.
And depending on how they choose to use that career break, technology runs past them. And then there is either a lot to cope up with or they give up. So, do you think there is some method in which they can update themselves while still
Yeah.
being on?
This was not possible. Like before COVID, this was not possible. Remote learning and remote work and everything did not exist. We Now there is a lot of opportunity because of the flexibility created in this post-COVID world. There are a lot of opportunities for women to have some remote internship. Let's say a woman has a maternity break, right? Obviously, she has to give time to the baby. That's important. But meanwhile, you can just, block out 1 hour of the day for some project that you're working on, or invest it something related to your career, or try to write a research paper if you're a researcher, or try to look out for opportunities. Just something you block out for your career, okay, like 1 hour, and you have to keep pursuing it. I don't think giving up should be an option. I know sometimes it gets very hard, and like for me things worked out because of family support really matters a lot for women during those breaks and after that especially. And then there are a lot of schemes for like post maternity. There should be nursing breaks, there should be on campus crèche and everything. So I think as women, we should be working hard. Women in those positions, they should be working hard to get those things in picture. And they should be actually, there should be women who are deciding these things for different institutes and different places, because if there are women out there, they know. And the women who are in that age group, let's say, because as you grow older, you tend to forget. Like I have forgotten what the hurdles were like a year back. Now it feels like up to sab kuch theek chal raha hai, now I don't need to play school. So that shouldn't be the case. It is alive in me, I have to work on it right now. Because And that's why such people should be a part of these committees, because they will vocalize it. They're feeling that pain that time, they will certainly vocalize it, and something might come up. As women, I think networking with women in your workplace is very important. Women who are going through these transitions, not before that, but certainly after, like if you have a baby or something like that.
So I'll take one last question because I think I had a candid conversation with you and only I know it. And I think it's worth having it here. Is that
Yeah.
I remember you saying that having children has changed you quite a bit. Like it has transformed the way you function. And I think,
Increase my functionalities, basically.
yeah. So would you like to shed some light on how, in terms of a teacher or in terms of a researcher, you feel the change and do you like it? Do you appreciate it? I would like
I
to know
think
a little.
becoming a mother is a huge, I don't think getting married is a change. Becoming a mother is a huge transition because the responsibility of the infant mostly is mothers, obviously, primarily because that's how God created it. uh, the mother is the person who basically has the baby for 9 months and everything. So I think women should be merciful to themselves in that time period. And after that, you do lose your functionalities, not in the sense because obviously you are putting your efforts and your mind into the baby, and obviously you can't be the same person in your research and career. But as a person now, my baby is 18 months old. I see that I'm getting back now. It took me some time, obviously, to get back, and my baby was needing me more. But now I'm getting back into my old self, maybe even better because I can multitask more as compared to before.
I wanted to ask if you are becoming less strict as a teacher because now you are a little bit softer. Because that would be something your students would really notice and tell you, though.
No, 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 I don't think so.
Okay.
That thing has remained constant. I'm not the strictest teacher. Sometimes I'm very friendly also, but it's just, goes up and down, I think.
Okay. So I think we have some time where I would encourage students to open their mics and ask any question that they want technical. There are a lot in the chat box. So I think you yourself can take these questions. Taiba, Dolly, these are some of the Vigyan students who are there in the forum today. And otherwise also, there are other students as well outside the Vigyan scholarship program who can raise their hands and open their mics. So please go ahead.
Someone has raised their hands. Shall I ask her to unmute?
Hi. I'm Sanskriti. It was very, very lovely to hear you speak about
Thank you so
your
much.
experience and the roadmap that you gave us. So, for me, the thing that I find the hardest while pursuing or practicing research is that I find it hard to balance things between fun and work because I am a person who likes to spend time with their friends or,
I am.
relax. So when you said that, you should be focusing on research or you should always have scientific discussions, how did you balance your social life? Because studies is not everything, right?
Yeah. So, looking at the presentation that I just gave, I think all of you must be thinking that all I've done in my life is study. That's not the case. All the pictures that I showed throughout are my pictures. I love photography. I love traveling. I love reading. So, and I have a huge group of friends from every phase of life that I went through. So, the thing is that the balance is the key, right? You have to have that balance. For instance, you know that you are a researcher, right? Now, as a researcher, you have to put in minimum 5. See, if you put in 3 focused hours into research every day, you are an excellent researcher, believe me. So you have to make sure that you put in some 3 or 4 hours, if possible, of um, of focused research, which means us time mein disturbance should be minimal. After that, you can go and with your friends and have your fun. But the time that you give to research should be focused. And I think even if someone gives 3 hours every day, that is a lot of focused research, I mean to say, which means you're
Mm,
actively thinking
yeah,
about it.
yeah. Thank you.
One of your ex-student is here,
Yeah.
Mahrukh. Please go ahead, ask your question.
Hello, am I audible?
Yes.
Yes,
Yeah, first I would like to congratulate for such a wonderful talk. And I'm
Thank you so
so
much.
proud of you. And thank you so much for being my guide. So I'm one of the first students that
Yeah.
ma'am taught. I've already written in the chat. I don't have a technical question. I just want to congratulate you.
Thank
And
you.
if you can allow an technical question, a non-technical question. So my question would be, how do you deal with toxicity in your environment, like people who demean you and who don't want to see you grow? So how do you deal with those people?
Well, that was the first batch of students that I taught. Maharukh is a PMRF fellow at IIT Bombay. So, can I address that?
yes, sure. Please
Cut
do.
out the noise. They are all noise. Everyone who is trying to bring you down is the noise. I know it's very easy to say cut out the noise. It will take you months to practice it. But a positive self-talk is very important. You tell yourself that this is toxic. First of all, don't even stay with those people if you have such people in your life. Come out of that friend circle, and then keep telling yourself, the conversations we have with ourselves are the most meaningful conversations we have in our lives, because what we tell ourselves, we become that. So if someone is saying bad about me and I keep ruminating over that, I will become that bad eventually. I mean, not maybe not as bad, but it will just manifest somehow. So you have to be away from those negative thought. So if someone is trying to put out negative talk about you, is trying to bring you down, first of all, you stay away from that people, and then you don't think over that. You just cut it out. It is going to take some time, but if you think about it, it's the art of thinking before thinking. जब दिमाग में कोई thought आए ना, उससे पहले ही you have to be like, okay, I'm not going to think in this direction. So once you master that, you will get there. But it will take a lot of training, and I have not mastered it. So we're all work in progress.
Thank you so much. Thank you. I'll try working on it. Thank you.
All the best.
Srishti, you want to go ahead with the question that you asked? Srishti Singh.
I read that question. What are the tough lessons you learned as the woman on the way up? So as a woman, I would say, there was nothing basically up until the maternity break that I took, the maternity leave. I faced no obstacle, which I would say was because I'm a woman. But after my baby, I just saw all the flaws in the system and the lack of mercy, I don't know, from men. Because I think that males, or basically all the stakeholders, are not aware of the laws which are out there for women who are in these transitionary periods. There are laws out there for nursing breaks. There are laws out there for flexible working hours also post COVID. So I think there should be awareness programs so that men in the institute also get to know that what are the rights of such women, and they do not trample on such rights. I think that was the hardest part for me. And the lesson that I learned was eventually that I should be vocalizing about those issues. I should try to, and I did try for a daycare center at NIT Srinagar. I did try for it, and they have built it up and everything. That is the toughest part that I had. But the lesson that I learned, I think the lesson more or less is persistence. You have to be persistent about things. Once you lose, no one is going to, no one is going to follow your dreams. You yourself have to do it.
Srishti, go ahead if you want to ask further on the same.
Yes, Srishti, please go ahead.
Good evening, ma'am.
Good evening.
Ma'am, currently I'm in my third year BSc. And right now, actually, I got into BSc under a lot of pressure. So I was not really looking to get into this, but okay, eventually I started liking chemistry as a subject. Now it's my main subject in my final year. So I like exploring a lot of different topics, but I wouldn't necessarily say yes that research is the thing for me, because I feel it requires a lot of understanding to get into it. So my question would be, ma'am, that if right now, since I'm just learning and understanding, what would be the first step I should take in order to understand if this is the right thing for me?
I think good books. Get good books. Now, I mean, I don't know. When I was a student, good books really helped. So if you get a good book which explains everything nicely, you might just end up, when you will understand those things, it might become your happy place. Can you repeat the question once again, Shrishti? What was the last part of what you asked?
Yeah, ma'am. I was asking what would be the steps I should follow in order to fully understand and get into this field, because I'm aware that this requires a lot of dedication and a lot of hard work, but moreover, it requires a lot of interest. So this is something that fascinates me, but I'm not sure if this is just a curiosity or something that I'm willing to work on.
Okay. So the way I landed up in research, I had not planned at all for research. I hadn't ever thought that I'm going to end up doing PhD. I had no clue about it. So I would suggest is, first of all, to understand the things that you're doing, you should be getting a good book, because that will help you understand things at a much better and a much deeper level. Which, and the thing about research is, hard work you have to do everywhere. About research is that the results may not be as quick as other jobs, or like you might not land up in lots of money or something like that. It will take, that persistence has to be there. Now what I would suggest is that, all these IITs, NITs, or even ISC, or somewhere wherever you live in and around that place, check out for internship programs. 2-month internship, people have that. So you can go there for 2 months and do a research based internship. That will give you exposure to what it is like, and based on your experience over there, you can figure out whether you want to go ahead with it or not. And even if you go ahead with it and you happen to realize after some time that it's not my way, that's okay. But at least you will know that you have gone down that path.
Thank you, ma'am. I would also like to ask that the books you were talking about that I should read, could you please recommend me something?
I don't know. I just remember there was a book in my class 12, organic chemistry. I don't know if you have organic chemistry, but there was
Yes,
this
ma'am. I
Solomon
definitely have
Fire
organic
or
chemistry.
something. That was an amazing book. I read a lot of that book. In my school days, I really loved chemistry and physics. I had these two amazing books. This was the Solomon Friel for organic chemistry, and then I had Resnick Halliday for physics. And it wasn't really so much about, for me, studies were not about, the con marks or anything. It was more about understanding for me. So if you have good books, if you have access to good literature, now we have access to everything because we have the computer. You can get some PDFs and start reading. And surround yourself with people who are into it. Go to libraries wherein you have a secluded place and you don't have distractions of phones. Phones are the most distracting thing. So I mean, I can't tell you, you guys are young, even we get distracted, even I get distracted. So you have to cut out that noise and then you have to focus.
I think
Yes,
there's
ma'am.
one student who has asked, Mohammed Zakaria Faruqi, who has asked about mental stamina. How do you keep positive even when you don't get any results and you are constantly trying at your work and you don't? So, how do you keep that mental stamina to keep up with the positivity? I think.
By reading positive things, by exposing, like I told Maharuk also, I think, by reading positive books, by exposing yourself to positive, and journaling helps. Now, I don't do all, now you might think I do all of these things. I don't. I'm not a perfect person who's not the best. I am where I am because of the grace of God. I would love to highlight that. Because, and with the help of people around me, it's God who gives you, but you should make sure that you work hard. It's God who gives in the end. But if you're working hard, and as long as you're working hard, the reward will come, the answer will come, the fruit of that hard work will come. It might not be in the shape that you see it. Sometimes we work continuously, no result is coming, but our perseverance is being built. Even that is a skill if if you look at it broadly. So mental
Pratiksha,
strength you maintain by journaling and writing positive things and being around positive people. Just positive self-talk. It will help a lot.
Pratiksha has asked some question. Pratiksha, I suggest you take it up yourself rather than typing it here. I can read it, but do you want to go ahead and ask the question?
I
Yes,
get
ma'am.
that question. Okay, go ahead. Go ahead.
Ma'am, I'm currently working on a book chapter and a research paper simultaneously. And what happens is I ran short of words very quickly when I start writing.
Hmm.
So, are there any suggestions which would keep
Okay.
me engaged
Using
in this
AI.
activity?
And you're saying using AI in research writing.
Yes, ma'am.
See, if I would not suggest that using AI straight off, because what I have seen my students do it, they use AI and they completely copy the answer, which doesn't make any sense. Now, obviously, the world is moving towards AI and we have to integrate with it somehow. Eventually, we all will have to come to terms with it. So, if you are using AI, you have to use it with your brains in it. So, if you're not able to write something, you can use AI, but you have to make sure that you don't copy it completely. If your idea is not in there, it's not you and it will come out. We have AI index, turn it in, just gives you straight away. Recently, I had to run a turn it in. A plagiarism report for someone, and the AI index was 71%. Now, obviously, people on the other side see that the AI index is so high, the paper won't get through. So you have to use your AI with your brains. and then you can use it to your benefit, let's say. So if you're not able to write something, writing is difficult. So I would say start with the results section, because results is something you got, right? You make those figures for your research paper, and once you have those figures in front of you, you can do descriptions of those figures, and after that you do the introduction, because introduction, I know, is a little, you get tired of it, but once you have the results, you will know that, okay, I'm closer to the end, so you'll do the introduction after that. I would suggest that.
Okay, ma'am. Thank you.
All the best.
So if there are no more questions, should
Ma'am,
we? Yes, please.
sorry, there is no hand raise option coming into my screen,
Sure,
but
sure.
I'll
That's
ask
okay.
the question.
Yes.
Sure.
I have one question, actually two. The one is related to research. Like, is it directly connected to how much research papers we publish make us a good researcher? And does it show that we publishing more research paper is more good work we are doing, or in a high impact factor paper?
I'm so sorry, someone called me in between. Can you please repeat the question once?
Yes, ma'am. I mean, like, if we are doing a research, and is it really necessary to publish more papers to prove that we are a good researcher? And also, does the impact factor that really matters? Because I have seen there are few papers where the impact factor is less, but the content they have given, the results they have got is more better than some of the high impact factor paper.
So the thing is, the research that you're trying to do, you should make sure that it's a good quality research. You work hard on it. You work hard on reproducing the results and all of that. And then obviously impact factor does not, as for some journals, it's not the impact factor because the name is good enough and the name itself works. But impact factor for other journals would matter. Like professionally, if you are going out there looking for a job, I think they will look for the impact factors, but they will also look for the number of publications you have. But the
Okay,
goal, if you keep those things as goal completely, you the goal I think you should keep as, I have to do good research and I have to get good results and I have to work hard on getting the output and everything. But also simultaneously you have to work on this thing, writing your papers. But I think sometimes what students do is they have a good paper and they divide it into three parts and publish three different papers. I would not suggest that. It's better to have one good paper than three papers with that work split out. That would be my personal suggestion to you.
Okay, ma'am. And my second question is not related to the research, but as a woman in, like, we all women are raising up. Thankfully, we got good supporting parents, but some or the other way into the working place, I feel there are still men who had that ego issue where they when they see a woman rising, they are always commenting onto the thing that how women should get married and settle down and be into an home. So have you ever faced that, and how do you tackle that thing? But like,
Gratefully,
being a
I
progressive
never
woman, we
had
have to
to.
be more.
Hmm. Gratefully, I never had to face that thing because I think the place I live in, the mindset is pretty different. But I do know that there are places where such a thing is there. Uh, so you have to work in that workplace. Obviously, you cannot just leave your job, but it's important to make the people around you aware that we are all equals. Now, I mean, we are all equals. Like everyone is the same. And if someone is having these conversations, if someone is vocalizing it that you should be at home, you should get married, you should do this, that, just ignore those people. I mean, just the fact that someone says that out loud just shows his or her, it will be his only. So it just shows his mental state. And you just have to ignore those things. I know ignoring those things are difficult. And for people who actually have such obstacles, they will have to work harder to come out of it. But once they come out of it, believe me, they will be so much freer to do what they have to do. And I don't
Okay,
think it's a
that
man's task to tell what a woman has to do.
true, ma'am. It is just a social thing that I've heard many of the time. Not me,
Yeah,
but my
usually,
friends too.
but
So
in your workplaces everywhere, I think females have this responsibility at some level to make men understand that we are not the same. So I said we're equals, but we're definitely not the same. It's the woman who bears the child for 9 months. So obviously a man does not do that. And therefore the reservations a women will have in that time will be different than a man. So all of these things have to be talked about, and people should not be ashamed of it, I think. People, women should not feel shy about it. These things should be discussed openly so that measures are taken such that such conversations are completely evaded.
I would like to thank Dr. Jalid for sharing her time and experience with all of us. It was such an enriching session. We
Thank you
wish
so
her many more successes in the future and hope for her continued support to the Vigyan program.
Yeah.
Thank you all to the students who have made the time to be here and be a part of this insightful discussion. The PKC team wishes you all successful future ahead. With this, I conclude the session and request all of you to give your feedback in the forms given in the chat box. And I think the certificates will be sent to you in about a week from now. So see you all in our next session in the next year, that is the new year 2025, and wish you all a Merry Christmas and Happy Holidays. Thank you all.
Thank you.